All right, welcome to Math 158, Functions, Graphs, and Matrices. We're going to look at section 2.2, Exponential Functions and Models. Okay. Before we jump in and we start going over the laws of exponents, let's go ahead and do a quick review of exponents. What do they mean and how do we operate with those? So the first thing I'm going to do, come over here to the left a little bit, do some work. I like to use the number 5. Okay. I'm ignoring anything that's going on my computer here. So 5 squared. I say to you, what's 5 squared? Very dutifully, a student says to me, it's 25. And I say, good, I'm glad you know that it's 25. That's the easy question. What about 5 to the third? An adventurous student says it's 125. Good, I'm glad. That's an easy question. A little bit harder is why. Why does 5 squared equal 25? Why does 5 to the third equal 125? Well, somebody says 5 squared is 25 because you do 5 times 5, or 5 to the third is 5 times 5 times 5. Okay, that's good. So I have an understanding of the application, but again, why? Well, 5 squared means that you multiply by 5 twice. Do I? For 5 squared, do I really multiply by 5 twice? Well, yes and no. If you multiply correctly, and this is something that even throughout this video, I'm not going to say this consistently because it's unnecessary, but it's important to understand, at least initially and foundationally, when you multiply, the fact that when you multiply, you always start with 1. So for example, even if I have 4 times 7, that still means 1 times 4 times 7, but 1 times 4 is 4, times 7 is 28. So we get away with not thinking about the 1. We get away without writing the 1. But, 5 squared does mean that you multiply by 5 twice, but it means that you start with 1 times 5 times 5. 5 to the third does mean that you start with 1 and multiply by 5 3 times. The exponent, okay, that's the exponent. It indicates if 5 is the base. The exponent 2, circled in purple, the exponent 2 indicates to me how many times I'm going to multiply by the base. 5. So I'm going to start with 1, multiply by 5 twice. So 5 to the fourth would mean that I start with 1, and then multiply by 5 1, 2, 3, 4 times. So 1 times 5 times 5 is 25. 1 times 5 times 5 times 5 is 125. 5 to the fourth is 625, and we could keep going if we'd like, but I want to go the opposite direction. 5 to the first, I would start with 1 and multiply by 5 once. See, that's why 5 to the first is 5, 4 to the first is 4, 18 to the first is 18, because you start with 1, you multiply by 18 once. I start with 1, and I multiply by 5 once. 5 to the 0, I say to somebody, what's x to the 0 power? What's 5 to the 0 power? What's 7 to the 0 power? It's 1. It's 1. It's 1. Why? Well, because so-and-so math teacher I had in the past said so. Well, I'm glad you remember them. Or by definition, it equals 1. Okay, so by definition of what? It's a definition of multiplication, quite honestly, because whenever you multiply, you start with 1, and now I'm going to multiply by 5 0 times, which means I do nothing. 7 to the 0 power, I start with 1 and I multiply by 7 0 times. It's really an indication of inaction. This is why anything, a to the 0 power, is equal to 1. I start with 1, I multiply by a 0 times. While we're here, let's keep going. What about a negative exponent? What does a negative exponent indicate? Well, sometimes the negative sign means negative. Sometimes it means opposite. Okay? Very closely related. You find -5 on the number line by going in the opposite direction, going to the left instead of to the right. So if I've got 5 to the negative first, what that means is I'm going to start with 1, and I'm going to do the opposite of multiplying. That's dividing. I'm going to do the opposite of multiplying. I'm going to divide. The opposite of multiplying by 5. I'm going to divide by 5 once. Or if I've got 5 to the negative second, that means I'm going to start with 1, do the opposite of multiplying, which is dividing by 5 twice. 1 divided by 5 times 5, or 1 divided by 5 to the third. This is why the negative exponent means division. It's not just made up. Okay, the exponent indicates how many times I'm multiplying. So if the exponent is negative, that indicates that I am dividing. So let's go back over and look at our rules, our laws of logarithms. Law number 1, b to the x times b to the y equals b to the x plus y. Well, suppose that we have 3 squared times 3 to the 4th. And again, at this point, I'm not going to write the 1 times, okay? 3 squared means I'm going to multiply by 3 twice. 3 to the 4th means I'm going to multiply by 3 4 times. So I've multiplied by 3 a total of 6 times. And so that's 3 to the 6th. Okay. B to the x divided by b to the y. Well, that would be like, let's suppose I have 4 to the 5th divided by 4 squared. 4 times 4 times 4 times 4 times 4, right? I'm multiplying by 4 in the numerator 5 times. I'm multiplying by 4 in the denominator twice. Well, now 4 divided by 4 is 1, and 4 divided by 4 is 1. Notice there are 3 4s left. That's 4 to the third, which is 64. Okay, so 4 to the third is 64. I subtract those exponents because 2 of the 4s in the denominator canceled 2 of the 4s in the numerator. Okay. Now number 3, we've kind of visited this already, right? So if I've got 5 to the negative third power, that means 1 divided by 5 to the third, or 1 over 125. Well, let's think about number 2 in context. If I got 4 to the 5th divided by 4 squared, 4 to the 5th is 4 to the 5th, but dividing by 4 squared is the same as multiplying by 4 to the negative second. Now notice I've got the same base 4 with those exponents. If I add exponents 5 and negative 2, I would get 3, and I would get the same value, 64, that I got up here. Number 4, we visited this one completely already. 8 to the 0 power is 1. 3x squared y to the 4th to the 0 power is, see, now everything inside is being raised, looking ahead a little bit to rule number 6, right? But everything inside the parentheses there is being raised to the 0 power, and so that would just be 1. Number 5 is related to number 1. Rule number 5 is related to rule number 1, but it's not exactly the same, right? So this one, suppose I have 3 squared, not 3 squared times 3 to the 4th, but 3 squared to the 4th power. That's the same as 3 squared multiplied 4 times. And at this point, I suppose I could just say, oh, that means I'm going to add the exponents. 2 plus 2 plus 2 plus 2 is 8. Or I can also take it up, I don't want purple. I can also take that a little farther, 3 times 3, right? 3 squared is 3 times 3. 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 1, 2, 3, 4, 5, 6, 7, 8. That's 3 to the 8th power. Number 6, the parentheses BC is raised to the x power. This means that everything inside the parentheses is raised to the x power, okay? We see this often earlier in algebra than this course, right? But if I've got 3x squared, the question I like to ask is what's being squared? Well, the 3 is being squared. the x is also being squared. And so that would be 9x squared. Now notice in the 9x squared, the 2 is on the exponent 2 is only on the x, so it's only the x that's being squared. Number 7, if I consider the fact that this exponent, x, applies to everything inside the parentheses, then in number 7, this exponent x applies to everything inside the parentheses, regardless of where it is. So suppose we have 5/3 squared. What's being squared? Well, the 5 is being squared, and the 3 is also being squared. So we've got 5 squared divided by 3 squared, 25/9. Okay, so there's a quick review of the rules of exponents. Moving on, let's consider that we have what's called an exponential function. We've kind of been working with expressions. What about an exponential function? An exponential function is anything that's written in the form y equals a times b to the x, okay? A is the initial value. B is the constant multiplier. It's a constant, and you constantly multiply by it. Now, in example 1, f of x equals 2 to the x. I can think of that as 1 times 2 to the x, where my a value is 1, my b value is 2. Okay? To do the substitutions here, it's much like we've done before. F of 2, I'm going to substitute 2 in place of the x. 2 squared is 4, so f of 2 is equal to 4. Negative 3, okay, is going to be 2 to the negative third power. Now, I've got the negative 3, so that's 1 over, right? We're dividing. We're doing the opposite of multiplying by 2 3 times, which means we're dividing by 2 3 times. And so that's going to be 1 over 2 cubed, or 1/8. So f of negative 3 is 1/8. Okay. F of 0, 2 to the 0 power, because we're going to put x 0 in for x, and so that's just 1. Now, 1D is a little bit tricky, right? Because we're going to do f of x equals 2 to the x, but we're going to replace the x with x plus 3. And the parentheses there are important. They're helpful, okay? I suppose I shouldn't say that they're imperative, but they are super helpful, okay? So now what I've got going on here is 2 to the x times 2 to the third. Remember your rules of exponents. 2 to the x is 2 to the x, 2 to the third is 8. So f of x plus 3 is equal to 8, parentheses are helpful, times 2 to the x. Okay, and so there's f of x plus 3. In number 2, okay, notice what we got going on here. Number 2, my a value is 2 and my b value is 3. Okay, so f of 2 is equal to 2 times 3 squared. 3 squared is 9, and so 2 times 9 is 18. F of 2 is equal to 18. That's crazy. F of negative 3 is 2 times 3 to the negative third power. Again, there's that exponent. Now, 2 is not being raised to the negative third power, right? 2 is outside the parentheses. 3 is being raised to the negative third power. So I've got 2, and I'm going to divide by 3 times. 3 cubed is 27, and so f of negative 3 is 2 over 27. F of 0, same way. I've got 2 times 3 to the 0. Notice that the 0 exponent is on the 3 only. So that's going to be, sorry about that. That's going to be, a little crazy, 2 times 1, which is 2. So f of 0 is 2. For f of x plus 2, we have 2 times 3 to the x plus 2. And I told you the parentheses around the exponent is helpful. This time I'm going to choose to not do it, just to show you that alternative, but just be careful. So I've got the 2 outside. Then inside, 3 is being raised to the x power times 3 squared, right? That's that rule number 1 in reverse. So we've got 2 times 3 to the x times 3 squared, which is 9. 2 times 9 is 18. We have 18 times 3 to the x. Okay, so f of x plus 2 is 18 times 3 to the x. Okay, so let's go on and let's look at graphing exponential functions. How do I graph an exponential function? We could go right to the calculator, I suppose, and just put one in. I guess, you know what, let's do that. Let's go to y equals, let's clear that out, 2 to the x. And let's just get an idea of what that's going to look like. It's always a good idea to hit zoom 6. That's your standard window. And you see the function here starts really close to the x-axis. It's not touching it. It's close to the x-axis. And the separation is slow at first, and all of a sudden this thing just takes off, and it increases exponentially. Okay. The calculator does a decent job of graphing the function, but it doesn't actually give us points unless we know what to go looking for. So let's look at how we would graph this function by hand. Okay. Now, by looking at this on the calculator, one thing we should recognize is that it's actually never going to touch the x-axis. If we go off in the negative direction, we put in negative values for x, that just means that we're going to be dividing by 2. And if I start with a positive number 2, and I divide by 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 2, I'll go from 2 to 1 to a half to a fourth to an eighth to a 16th. And those numbers are getting smaller and smaller and smaller, but they will never actually get to the 2. Make this straighter. Sorry, never actually get to 0. So what's going to happen here is we're actually going to have a horizontal asymptote. We're going to have that horizontal line that function will not ever get to, will not ever touch. Okay, so now when I go to graph this, let's make a little table of values, I suppose. I don't know if I want to do this every time, but we'll do it at least a couple of times. I like to pick 0 and 1 for x. If x is 0, f of x is 2 to the 0, which is 1. If x is 1, f of x is 2 to the first, which is 2. Let's go one more. 2 squared would be 4. So if x is 0, let's go 0, 1, 2, 3, 1, 2, 3, 4. If x is 0, y is 1. Always label the point. That's 0, 1. If x is 1, y is 2, and that's 0.1. 2, I suppose we'll go one more, and that's 2, 4. Now, if I look at the calculator and I see what the graph is going to look like, and I know it's an exponential function, even 2 points, 3 is better, but we get an idea. Oops, I missed the point there, didn't I? We get an idea of what that function is going to look like. And you know, my pictures aren't pretty, but it is a good sketch of the function. Okay. Number 4, x-axis and our y-axis, we'll get those graphed. Again, positive number, positive number. We're going to start with a positive number, keep multiplying or dividing it by a positive number, so it's always going to be positive. So horizontal asymptote again. And let's go ahead with that t-chart, table of values. If x is 0, we're going to have 2 times 3 to the 0, which is 2. If x is 1, we're going to have 2 times 3 to the first, which is 6. So when x is 0, y is 2, it's not sufficient to just label that as 2, because the way that I know the graph is going through that point, is by actually labeling the coordinates of the point, in this case, 0, 2. 1, 3, 4, 5, 6. So that'd be 1, 6. That's the point 1, 6. And our graph is going to look like this. Okay? And so the graph is plotted. Now, in number 5, let's go ahead and cheat with the calculator. Not cheat. Let's just use technology to our advantage, right? So we're going to have 1/2 to the x power. Right? That's the function 1/2 to the x power. If I graph that, notice that the graph is coming down instead of going up. We're going to multiply by 1/2. So we're going to have 1/2 times 1/2 times 1/2 times 1/2. We're going to go from 1/2 to 1/4, 1/8, 1/16. Like I said before, always going to be positive. We're going to have a horizontal asymptote. But now when I go to make that table of values, if x is 0, we're going to have 1/2 to the 0, which is 1. Notice that keeps happening. And if x is 1, we're going to have 1/2 to the first, which is 1/2. So we've got 0, 1. And we've got 1, 1/2. Those are those points. And then our function is going to come down. Whoops. Our function, let's undo some of that. Our function is going to come down like this. And there's a decent sketch of the graph. And notice, because I know it's an exponential function, I understand what the curve is going to look like. I can get away with labeling or identifying only 2 points before I go ahead and sketch the curve. I have our horizontal asymptote. Note if x is 1, if x is 0, we're going to have 2/3 of 0 is 1 times 3 is 3. So there's our point 0, 3. When x is 1, 3 times 2/3 is going to give us 2. So there's our point 1, 2. And we have exponential decay again. So there's the term exponential decay. Notice that in numbers 3 and 4, the functions are getting larger as x gets larger. We're going up. These are exponential growth. Notice that the b value is greater than 1. Therefore, we have exponential growth. Okay. In number 5 and number 6, our b values, 1/2 and 2/3. Those values are less than 1. So what we have there is exponential decay. The functions are getting smaller. So here's some characteristics of graphing functions. Okay. An exponential function will always have a horizontal asymptote. The graph will always go through the point 0a and 1ab. Every time. Every time. If you notice, in this function, a is 1 and b is 2. Here's the point 0a, and here's the point 1ab. 1 times 2 is 2. In number 4, a is 2, and b is 3. Notice our 2 points are 0, 2, and 1, 6, because a times b is 6. In number 5, our a value is 1, our b value is 1/2, so ab would be 1/2. Notice we have the point 0, 1, and the point 1, 1/2. In number 6, our a value is 3, our b value is 2/3, so ab would be 2. Here's the point 0a, and here's the point, here's the point 1ab. Okay, it's going to work every time. So, graphing exponential functions. Okay, so let's move on to, whoops, wrong direction. Looking at finding an exponential function given 2 points. Okay, so what I want to do here is we're going to work on this algebraically, and then we'll also look at how to do it electronically on the calculator. Okay, so find the exponential function that passes through the 2 points, 212 and 596. Recall that the exponential function looks like y equals a times b to the x. So what I'm going to do is, just like with the equation of a line, I'm going to take the 2 points, 212 and 596, and I'm going to substitute them into the equation for x and y. I do like to start with the equation that has the larger x value, or the point that has the larger x value. So the y value is 96, and that equals a times b to the fifth. The other point, 212, y is 12, and that equals a times b squared. Okay, when I'm finding the equation of a line, I would subtract the two equations because I want to subtract out the b values, right? And y equals mx plus b. Here, what I'm going to do is I'm going to divide both sides of the first equation by each side of the second equation. So 96 divided by 12 is 8. And a divided by a is 1. B to the fifth divided by b to the second is b to the third. Okay? And so we can just know that if b to the third equals 8, that b would equal 2. Now, there's going to be problems in the future that we won't just know that the cube root of 8 is 2, or 2 to the third is 8. Here's what I think is going to be the best way to process this with the calculator. I want this to be b to the first. So I need to raise the right-hand side of this equation to the 1/3 power. So I have b to the third to the 1/3 because 3 times 1/3 will give me the 1. But if I raise the right-hand side of the equation to 1/3, I need to also raise the left-hand side of the 1/3 power. I'm going to come to my calculator and simply do 8 to the 1/3 power. And that would be 2. So b equals 2. So it's good to be able to see some of these and know them. But it's also good to be able to figure out how do I get this using the graphing calculator. So b to the first is equal to 2. Or I can just write b equals 2. Okay. So now how do I find a? Well, I'm going to take that 2 that b equals and substitute it for b in either one of those two equations. Personally, I like to put it in the one with the smaller numbers. So 12 is equal to a times b, which is 2 squared. So 12 is equal to a times 4. Divide both sides by the 4, and a will equal 3. So now we know that b is equal to 2, and a is equal to 3. So y is equal to a times b to the x power. And there is the equation, the exponential function that passes through those 2 points. Okay. Now I'm going to skip number 8 for a moment. Come back to number 8. Number 9, I want to look at number 9 first, because notice this point here is 0, 15. Now, if I just jump in and do this one the same, you say, okay, I'm going to jump in and do, Professor Jensen, I'm going to jump in and do this the same way you did, number 7, and I'm going to start with this point here. So in y equals a times b to the x, okay, so we'll put 25 equals a times b to the 10th. Okay, you can do that. Take this point here, the 0, 15. So when y is 15, we have a times b to the 0. Now this is unique because we know that b to the 0 is equal to 1. And so we have 15 equals a. Well, if I know that you've got x is 0, that tells me that my initial value is 15. I can see from that point that my a value is 15, and I could have just started with y equals 15 times b to the x. And now into this equation, I'm going to put the 0.1025. So b to the 10th is equal to 25 divided by 15. Now, I could do 25 divided by 15 as 5/3. That's fine. You can do that. But to solve this for b, I'm going to raise both sides to the 1/10th power, just like I showed you already. And so b will equal, I'm just going to leave it 25/15 to the 1/10th power. And I get 1.052. So b is 1.052. So my equation is y is equal to a, 15, times 1.052 to the x. Okay. If you wanted to try to turn that 1.052, if you want to try to change this back to a fraction, we could go to math, and number 1, we'll try to change this back to a fraction. I doubt it will work. No, it doesn't work. So rounding it to 3 decimal places is fine. Okay. So for number 8, I get into this one with fractions, and I'm thinking to myself, do I want to handle the fractions? I know you do. But here's another option that I want you to see. Stat, edit, into the, just like we did with linear regression and quadratic regression, I'm going to put my x values, -2 and 2, into the L1. And I'm going to put 20 and 5/4 in for my x values. Stat, calc. Now, if I go down my list, number 4 is linear regression. We've seen that before. Number 5 is quadratic regression. We've seen that before. We want to go down all the way here to number 10, or 0, exponential regression. X values are in L1. My Y values are in L2. I'm not going to bother storing the reg-EQ because at this point, for this problem, all I want is to know that the equation, calculate. Oh, it turns out to be fairly simple. So Y, where we go? So Y is equal to A, which is 5, times B, which is, okay, 0.5. You can write that as 1/2 to the x. And so there's the equation. It turned out to not be nearly as complicated as I had thought it might. Okay. But I can use the calculator as an option there. Okay. So number 10, let's look at some applications. Okay. A lot of conversation these days about minimum wage. We're not going to get into the argument, but I do think it's important before we just say, I think this, or I feel that, or I know this will happen, or I know that won't work, that won't happen. This has been true, this has not been true. It's really, I find it interesting to actually look at some data, okay? So the minimum wage, a little historical perspective, the minimum wage was established in 1939 at 25 cents an hour, okay? 25 cents an hour. Remember having conversations with my grandfather about working for about that much money. Do the math. 25 cents an hour, and you work 40 hours a week. Whoops. You're making $10 a week. Of course, we're talking 1939. In any case, in 1939, the minimum wage was 25 cents or $0.25 per hour. Currently, even though it's up for debate right now, every couple of years we bring it up for debate, in 2021, the current federal minimum wage is still $7.25 an hour. Some states have raised it, I get that, but the current federal minimum wage is still 25 cents an hour. So I want to find an exponential function that models the federal minimum wage as a function of time. First thing I'm going to do is I'm going to say, you know what, I really don't want to find the minimum wage since year 0 and let x represent the number of years since year 0. I'm going to choose to let x represent the number of years since 1939. That would make 1939 year 0. And that would make 2021 year 82. So when I do this, right, so y equals a times b to the x, even though I can use my calculator, even if I, by the way, use that exponential regression, I would still make my years 0 and 82, not 1939 and 2021. So because 1939 is year 0, we know that 0.25 is A. Remember what we said A is. A is the initial value. The initial minimum wage was 25 cents or $0.25 per hour times B to the X. Now I can take my second point and put those values in for X and Y. And so 725 is equal to 0.25 times B to the 82nd power. If I divide both sides by the 0.25, B to the 82nd power is equal to 7.25 divided by 0.25. And then we're going to raise both sides to the 1 over 82 power. So on the left-hand side, these will cancel, and I'll get B to the first. And so coming to our calculator, 7.25 divided by 0.25 raised to the 1 over 82 power, 1.042. So y is equal to 0.25 times 1.042 to the x. So that is the function that would give me the increase in the minimum wage as a function of time. Assuming it's been an even increase. We know that it's more of a political issue, and every once in a while it gets raised by $1 here or 50 cents there. Of course, now we're looking at a raise significant to the minimum wage. But at this function, at y equals 0.25 times 1.042 to the x, what's the average annual rate of increase? Assuming the minimum wage has been increasing in the same amount, we're going to look at this 1.042. That 1.042 is our multiplier. We can think of that as 104.2% of, not more, but of. I take 0.25, multiply it by 104.2%, 1.042, which means each year I have my 25 cents. Each year I have 100% and 4.2% more. So my increase is 4.2%. From my 104.2%, I'm subtracting 100%. And so I'm looking at an average annual increase of 4.2%. Okay, so I hope that 4.2 makes sense. In the conversation about minimum wage, that's a piece of data I bring into the conversation. Hey, what's the rate at which the economy's been increasing? What's the rate at which the minimum wage has been increasing? Do you realize that the minimum wage has actually historically has an average increase of about 4.2%? Okay. Again, not that it settles the conversation or even my opinion. I'm not even sure what my opinion is on the issue because I like to explore the data, but that is a data point that I bring into the conversation. All right, so let's move on. And let's talk for a moment about growth and decay before we do two more application type problems. 11a. Notice that our B value, let's fix this. Notice that our B value is 1.156. Since B is greater than 1, this is exponential growth. Notice here in part B, our B value is less than 1, so we have exponential decay. That's the easy part here. For each one of these, indicate whether we have growth or decay. A is growth, part B is decay. What's a little bit more tedious, what's a little bit more involved, is what is the rate of growth or the rate of decay. Now in part A, at 1.156, I said we can think of that as 115.6. So we're going to subtract 100. So that's a growth rate of about 15.6% per year. Wouldn't that be nice if your investment increased 15.6% per year? Suppose you have an investment, right? Let's look at this. Suppose that you have $1,000 in the bank, and each year it increases by 15.6%. The easiest way to handle that is not to find 15.6% of that and add it to 1,000, but would be simply to multiply it by 1.156. So after 1 year, 2 years, 3 years, 4 years, that's the growth rate of your investment. Okay. Now in part B, notice if I start with 15.6, right? We're starting with 15.6. The value of your car, let's say, is $15.6 thousand, and the value of your car drops. And so it's going to decay because each year we're going to multiply the value by 0.853. And notice the value is decreasing, exponential decay. But what is the rate of decay? I think what's easy for part A is we can say, oh, look, here is the 15.6% increase. With the minimum wage, we could do something similar. You don't see that quite so obviously with exponential decay. But this is why I wanted to take the time and do this part here. 0.853, I can think of that as 85.3%. I'm going to subtract 100% from that, and I get negative 14.7, right? 85.3 minus 100, negative 14.7. So that's the decay. The negative indicates decay. My rate of decay is 14.7%. So I'm going to decay. For the value of my car, let's suppose, is going to decrease 14.7% each year. Okay. So exponential growth and decay can be used when talking about finance. Okay. We're going to look now at the exponential function, kind of anticipating moving forward. Just looking at these kind of clean. We're going to get a lot more involved in Unit 3 into the aspect of finance, and the application of exponential functions will be a lot more involved in Unit 3 than we'll do right here. But right now, we're just going to look a little bit ahead, just a little bit. Consider the function y equals a times b to the x. A here is future value, amount in the future. Sometimes you'll see FV used, not F times V, that's just FV, future value. Okay, that compares to the Y value. P is principal, present value, how much money you have presently. That corresponds to the initial value A. 1 plus R over N corresponds to my B value. And then the exponent NT corresponds to the X. So really, this is just a applied use of y equals a times b to the x. Okay, so if I'm going to invest $2,500, that's P. Into an account earning 7.2% interest, that's R. Compounded monthly, that's N. What will my account be worth in 15 years? That's T. So I want to know, A, what will my account be worth in 15 years? My principal is 2,500 times 1 plus 0.072 over 12 to the 12 times 15. All I did is I took those values and substituted them into each particular place. I'm not going to try to do this without the use of the calculator. So 2,500 times 1 plus 0.072 divided by 12 to the 12 times 15th power. It's 180 if you care. And so the future value of my investment will be $7,337.98. How many decimal places should you go? We're talking about money, so 2 decimal places is good. Okay. Now, if I had a big whiteboard and we're in the room, we're together, I'd probably take some time to derive this function for you from here. Basically, what happens is as n approaches infinity, as we invest more and more and more frequently, our interest is compounded more and more frequently, rather than compounding our interest monthly, weekly, daily, minutely, our interest is being continuously compounded. What happens is this value, 1 plus r over n to the n, that approaches e to the r. And so what you'll notice is that we essentially, in this function, we have essentially replaced, not essentially, exactly, 1 plus r over n to the n has been replaced with e to the r. Now e, okay, I can look at my calculator to get a good picture of it. Notice right here above the division sign is the e. That's the number 2.718281828. It appears to repeat, but it does not. Okay, so if my interest is going to be compounded continually, I use this function a equals, so this equation, a equals p times e to the r t. And again, 2,500 is my p, 7.2 is my r, 15 is my t. No n, because we're not compounding periodically, we're compounding continuously. So the amount of the investment, same investment, $2,500 at 7.2, forgot a zero there, at 7.2% interest, compounded continuously for 15 years, 2,500. Now, to do times e to the r, I'm not going to use the e here on the division. Notice the natural log here to the left of 4, second e to the. That automatically gives me an exponent. 0.072 times 15. So that would be 7361. 70, yeah. So notice that my investment is slightly more if I invest in my interest in an account compounded continuously as opposed to compounded periodically. Okay, so let's look at one more example. Okay, this table gives us the cost of college tuition for all 4 public and private colleges from 1980 to 2010. Okay, I mentioned before something about minimum wage, and another piece of that conversation I have is juxtapose that against the rising cost of college, right? Because those two, if we argue that minimum wage should be kids who are saving for college, well, then we need to look at those two in tandem. Again, I'm not making an argument for or against minimum wage. I'm just simply talking about data points that I'd like to actually bring into the conversation. So similar to what we've done before, I'm not going to talk about the cost of American college since the year 0, because that would be silly. I'm going to let T, okay, I'm going to let T represent the number of years since 1980. So 1980 would be year 0, 1990 would be year 10, 2000 would be year 20, 2004 would be 24, 28, and 30. Okay, so if I go to Stat Edit, I'm going to put these data points into my calculator. So we've got 0, 10, 20, 24, 28, and 30. Those are my X values, my T values. My dollars, my cost, my Y values are 3,500. $76.02, 12,922. I remember when I went to college having the conversation about how expensive college was. And my first year of college at a private live-on-campus school was about $5,000. Okay, so we've got our college tuition costs. This is tuition, right? Use the TI-84 to produce a scatter plot. Okay, so if I were to go to second stat plot, we want to choose number 1 to turn the plot on. We've got the scatter plot, L1 and L2. And again, I said to you, I like the pluses. I'm going to go back to my Y equals and just get rid of that guy. And then now before I go to do the scatter plot, like we've done before, I'm going to go to zoom 9, do a zoom stat, and I can see the scatter plot. Now, if I'm going to draw that, if I'm going to try to give some hand-drawn semblance or resemblance of that, you know, if I just say, okay, we've got like here, that's kind of what the table looks like to me. My years are going from 0 to 30. My Y value, we're going from, let's look at the window, we're going from 355, let's call that 0 to $25,000. Okay, so I do need to have some scale on here. Would a linear model be best for this data? Why or why not? Well, it would not be, because in a linear model, you're looking for a constant amount of increase. And you can see that in that 10 years, that was an increase of $4,100. In this 10 years, it was an increase of $5,300. Now be careful. In this next 10 year, it's an increase of $11,000. Okay, so every 10 years, you're not increasing by the same amount. So linear model is not a good model for this data because you don't have a constant amount of increase. Okay, no, the amount increase is not consistent. Okay, now to find the exponential model for this data, we've kind of already done it, right? Stat calc, we're going to go back to number 0, the exponential regression. Press enter there. My X list is in L1, my Y list is in L2. When I did this before, I think it was problem number 8, I didn't bother to store the reg EQ because we weren't going to do anything with it. We are going to do more with this regression equation. So I'm going to store my regression equation into Y1, and we're going to calculate. So our cost of tuition, I'm going to put tuition as a function of time, is equal to $37.68. Let's just round to the nearest dollar since we're talking college. $37.69 times 1.063 to the X, right? So my B value is 1.0625, 1.063. Okay. Now, does the exponential model fit the data better? Sure. Notice how it curves with the data and hits most of the data points. Now, I want to use the regression model to say, well, what would we have predicted the cost of college to be in the year 2020? one of the ways I've shown you to do this, right, would be to go to the table. So make sure if you go to second table set that your independent variable is on is on ask. Second table. Now I can substitute in values for x. Based on the model, if x is 0, we would predict that according to this model, that in 1980, the cost of college was approximately $37.69. Okay. In 2020, well, x equals 0, or sorry, t equals 0 was 1980. So in this case, this would be 40 years. Okay. T is 40. We would predict that according to that model, we would predict in 2020 that the cost of college was $42,606. Okay. Probably not so far off. Now, this shows, by the way, let me go back, that college has been increasing at approximately 6.3%. So that's the other piece of data, right? I mentioned, that minimum wage. Somebody argues with me, well, it's high school and college kids who should be starting out working minimum wage jobs. Okay, and minimum wage has been increasing faster than the rate of the economy at 4.2%. Yeah, okay. But the cost of college, the things that they should be paying for, has been increasing at 6.3%. Another piece of data to bring into that conversation, because again, I like having complete conversations, not single topic conversations. So just the math of that, cost of college, according to this data, has been increasing at approximately 6.3%. Well, that's interesting. Okay, now I like to look at students and say, is it your parents' obligation to pay for you? Because let's think about this. Use the regression model to estimate the cost of college when you will be sending your oldest child to college. Now, I don't know how old you are, and I don't know how old your children are, if in fact you have children. For me, I'm going to use as an example my grandchild. Okay, I have a grandchild who's a month old, and so she'll be going to college, 18 years from now? That would be the year 2039. So in 2039, T would be 59, right? Because that's 59 years after 1980. Okay. Well, let's try that. Oops, not 599. 59. I'll be talking with my daughter soon. I'm going to tell her that she can expect that when her oldest goes to college, if things don't change, we would predict that the cost of college will be $134,827. We could probably call that $135,000 per year, if the model holds. Okay, now one last thought here in conclusion. A number of people say to me, well, you can't predict it because there's no guarantee that it's going to continue to increase 6.3%. You're right, I can't. But I can't also make an assumption of what else it will be. The prediction is, if the model holds, if college continues, over the last 40 years, college has increased at a rate of approximately 6.3%. If the cost of college continues to increase at 6.3, approximately 6.3%, then we would predict that in 2039, the cost of college would be just shy of $135,000 per year. Hopefully things will change, but that is what the prediction will be. Okay, so there's a look at exponential functions, regression, as